I think as a scientist, now you realize that gravity is universal. There's no one who is shielded from gravity. Once you start thinking of it like that, you wonder, why would you think of anything else? I think we wouldn't be here as human if we thought, okay, that's it now. It's really important to push ourselves in our horizon. And I see the space exploration as being crucial in that.
Few hours may pass, when you're very close to a black hole, while centuries may pass when we are on Earth. As gravity gets stronger, it is able to kind of hold back time in some ways.
Absolutely, that's what it is. If someone comes along and say, hey, look, I have something new here, how about we think about that? We start wondering, okay, hold on a second. Have you thought about all of the things? I think some level of skepticism is important. There is not as many women as would be actually beneficial for research, beneficial for the driving of research. Doing research in a more diverse way is just pragmatically the best way to do research. That is the bottom line.
Claudia, welcome to SparX.
Hi, thanks a lot.
Yeah, really looking forward to this conversation. I read your book, Beauty of Falling. In fact, I have the book right here with me. I have to say, this is one of the most enjoyable physics book I would have read in a long time. It's great that, you are weaving kind of your personal journey as well as pretty cutting edge research in theoretical physics. But first of all, let's start with the title, Beauty of Falling. For most of us, falling is painful, whether it figuratively or metaphorically, but we talk about how falling is inevitable part of life and part and parcel, and you kind of so eloquently talk about. So why this title, Beauty of Falling?
I think it is. It is a little bit of a joke in that idea that we do think typically falling is something bad and we're scared of it. But it's very much in showing that there's a beauty in it. For me, there's a beauty in the scientific journey in discovering what the laws of nature are. And there's a part of failure there every day. That's how we learn, just like that's the way we learn to walk, by falling down. And that's not something we should be scared of. It's you just embrace it a little bit and you play along, and then that's how you move forward. So there's a little bit of that aspect of embracing this aspect that you have to fail a little bit to make progress, and that's actually what led us to where we are. Not everything has been straightforward in our evolution as human being, in our evolution in the scientific journey, discoveries of understanding everything around us. There's also, of course, the beauty of falling itself in the sense of the beauty of gravity, which is what I study, what I research. And it is such a universal phenomenon. To me, it is so beautiful. It is so universal. It really connects us all together. So there's a real beauty in that. I think there's another aspect, which is we think of falling as something which is negative because we think of what happens after the fall when we hit the floor. That is what was negative. But the fall itself, if you imagine when you're in a parachute falling or when you're in free fall, in itself, it's really a very blissful experience. There's a real beauty in that, and there's an ability to extract yourself from anything else and just embrace that experience. And that in itself has, I think, a fundamental beauty in it that we can all connect to.
And what's amazing about your book, Claudia, is that you weave in the story of both your progress as a scientist and studying gravity fairly seriously. In fact, contributing some really breakthrough understanding of gravity, which we'll come to that later. But also in some ways, your own personal journey in quest to, in some ways, to defy gravity as much as possible. In fact, I think there's everybody in the world who at some point, especially as a kid, dreams of being an astronaut, but you actually took it very seriously and pursued for quite a long period of time. So I think for, among our listeners, people who are maybe youngsters who may dream of being an astronaut, or parents who may have kids who might dream of being an astronaut, what does it take to actually seriously pursue, and not it just being a pipe dream, but actually putting the effort, which you did for a couple of decades, if I'm not mistaken. So can you just take us to the journey of that dream and then this commitment to pursue that so seriously?
Yes, absolutely. It was very much a commitment, but I have to say it was a commitment I was willing to do because I was seeing as part of the exploration. At no point did I do something I didn't feel like I wanted to do just for the sake of it. It's very much all of this connects together, all the experiences, everything I have learned in the journey to try to becoming an astronaut were things I would have wanted to do them on themselves. So, for instance, I started scuba diving from a very, very early age, before even I was allowed to as a kid. And it's not, to me, something disconnected to the scientific exploration. It's very much embracing it as well. Like you embrace the free fall, you embrace the experience and the adventure. When you go scuba diving, it is a way as well to put yourself in a completely new environment and then just adapt to it and realize how you can actually be connected to this environment, how you can appreciate it at a different level. So, of course, that's quite different to the scientific exploration I do on my everyday research, like on the blackboard behind me. But conceptually, it still is part of the same exploration. So I went through all of the stages, not only learning to scuba dive, but also being a dive master and teaching other people how to scuba dive, because it's also part of this, not only doing things for yourself, but also doing things for the others. And it's in connecting with the others that you appreciate much more how things are working. So that was one of the aspects. Another aspect I've done as soon as I could, that was much later, but it was learning to fly, which I absolutely loved, really. For quite a long time, I thought, well, if this astronaut dream didn't work out, and if research didn't work out, then I would become a professional pilot. And I think I would have been quite happy, because it's just such a beautiful experience to fly. The plane I was flying was a single engine, a very, very tiny thing, so small you really completely crunch. But it was also such a blissful adventure. For me, it was very much a step towards exploring and understanding how you can defy gravity to some extent, but also because it's also one of the aspects that would help becoming an astronaut. Then I did a lot of other things, which I don't know in retrospect whether it was useful or not, but there's a lot of dexterity involved in becoming an astronaut. I did write when I was a kid to astronaut Claudia de Rham, who was one astronaut that did something spectacular under the Hubble telescope, actually. And what he told me, he responded to me, it was quite a while ago, he responded to me and he said, really just be crafty. And actually, that's really important. Be crafty and keep your curiosity alive. And I think that is the biggest advice I would give to anyone else as well. Being crafty in the sense that anything you see around you, just try to connect with it and seeing how you can actually play with it or adapt to it. Because of course, if you are an astronaut, you're out there, and then you're not going to call someone to help you for something. You need to fix everything yourself. But it's part very much of engaging with seeing how you can actually yourself be part of the solution. It's very much part of this. Yeah.
Right. And, so in your 20s and 30s, you were trying to establish yourself as a theoretical physicist, going through a PhD, postdoc, etc. But, will require a lot of intellectually pushing, your boundaries. But while training to be an astronaut in future, you're also pushing your physical limits and learning lots of skills and being crafty, as you say, like, being able to, that must take a lot. I mean, it's not every day, come up with somebody, you're able to simultaneously push your boundaries. How did you, manage that? Is it something was innate, you wanted to, be in the situation where you're continuously pushing and seeing what the boundaries are, or you train yourself, because sustaining that drive and two somewhat very different directions, it's very, very unique and rare.
Yeah, so I think it is important that the drive comes from you and you're not doing it because you feel you're forced to, and you set up yourself a journey and then it's almost forced from the outside to follow those steps. It's all of these things, as well as being a theoretical physicist, it requires a lot of inner drive, and you have to do it because the motivation comes from you, because you're enjoying it. So I only ever been doing things I actually would have enjoyed, would have wanted to do them on their own, irrespectively of any dream, irrespectively of anything else. I think this is very, very important, and it helps. I think it's true that many of the nights were quite short because I would wake up very early to go flying, and then when the actual day of the working day started, that's when I went back to work, and I started my day as a theoretical physicist. I think this balance between the two did help each other. I think being able to extract myself and being in a completely different environment, focus on something very concrete, actually, very pragmatic. Flying a plane, it has to be very, very pragmatic. There's no, how do I feel about how I want to land? No, you have to follow the procedure. It's like that. And you have to focus. But I think that does clear your mind in a way that you're much more efficient and you see things much more clearly afterwards. I remember a lot of the time I would drive to the airport and I would be thinking about a theoretical problem in my mind, some of the research. And once you're in the plane, all of this goes away. You don't have bandwidth to start thinking about those things. You're very, very focused all the time. But then I would land and then I would drive back home. And then all of a sudden, lots of ideas would come up about the research. I think it does help a lot to sometimes, it's almost like meditation, I would say.
Right, great. So, your pursuit of astronaut training, help you develop a lot of different skills. And as you say, also helped you with your core work because you are able to disconnect completely and be in very different environment and totally focused, right? And, probably are able to process things and synthesize things and go back with better ideas to your daily work as well. Right.
That's right.
And you went pretty far. It was not just you were training and dreaming. You pursued that quite seriously, and it's probably for not and look, there are unfortunately very few astronaut positions available in the world today. Hope that will change in the coming decades. But today you have to be literally handful of people in the whole world, and luck also plays a very big role. But you went very far and this close to potentially being an astronaut at a European Space Agency, right?
Yes. yeah, very, very close. Yeah. So throughout the progress, throughout the decades, really, where I had put it in my mind, this is what I want to do, and it was clear in my mind that the chances were very, very small. I was quite realistic. I'm a scientist after all, and I knew the chances were very small. So it's not like I put all my eggs in that basket and thought, okay, that would be it. And if not, there's no way out. I did have another career as a theoretical physicist. And as I say, I would have been happy being a pilot as well. That was okay. But as the selection started and as I went along, it was a very, very long process of a year, more than a year long. So as the different stages went through, it started becoming more and more concrete. And as well, throughout the selection process, when I had some interviews or I had some meetings, it was with more and more specialized people who were also telling me, okay, this is a situation, and made me aware that it was becoming more and more realistic. So then the dream became a bit more alive, and I think the fall hitting the ground became a little bit harder when reality hit, when finally I went back on Earth and realized it wasn't possible, but it was to the very, very end, at the last possible stage. It's part of the adventure. It's part of the journey. I don't regret anything. Absolutely. I don't regret anything at all.
Right. And for people who are curious about how far you went in the journey and eventually at what stage you stop, I think we'll let them read the book and get more details on that. We have so many other things to cover. But last thing on this bit, do you think, so look, space gets so much attention these days, and we have, fortunately, many private space companies as well. In fact, there is one I'm involved in India, Skyroot, which is building rockets and had their successful suborbital launch last year. Do you think in the coming decades, this whole talk of space tourism or in general, will we see astronauts going back to moon and so on? What is your understanding of is that? Because it's been quite slow overall last many decades after, all the euphoria in 60s and 70s. But do you think it's going to change in coming decades?
Yeah, that's a good question. And I think it's true, it's been quite slow and it's been much more pragmatic, much more in terms of what needs to happen as opposed to let's explore. I think there is also all the climate crisis that you do wonder, and people ask me all the time, does it make sense to spend all this energy, to spend all of this endeavor towards space exploration when we should actually just look at ourselves on Earth and make the most for the current situation? I think what is true, it is never one way, and if we want to help with just the climate crisis and lots of other crises, we do need all of this space exploration in terms of understanding our own Earth as well. So it's not like we can just focus on one development and not another one. I do think following some space exploration, if we had some resources on the moon, particularly on the other side of the moon, who knows how much further we can go. And so it is important. It is important never to stop. I think we wouldn't be here as human if we thought, okay, that's it now, and we're happy where we are, and we're just going to focus on our own localized problems. It's really important to push ourselves in our horizon. And I see the space exploration as being crucial in that. So I very, very much hope it's going to continue driving, but even faster. So thank you for exploring all of this. I think it is important. Yeah.
Yeah. No, I'm also very optimistic. Hopefully, in the coming decades, I think humanity as a whole will decide to invest more in space exploration. The space is vast. But let's come back to gravity, Claudia. So at some point, you decide to pursue research in gravity. Was it like a love at first sight with gravity? How did you arrive at because gravity it's in some ways it's fascinating. In some ways a general theory of relativity has pretty much kind of given us all, in some ways we needed to understand gravity at a very, very macroscopic scales, and it has been brilliantly useful in solving so many things and predicting so many things. So what is it about gravity, that convince you that there are things that are yet to be, that are both unsolved, and you had the confidence that something, you can make a dent in that space? Just talk about in that journey of committing that path.
Yeah, those are great questions. I think if you were to ask me 5-6 years ago whether gravity was love at first sight and what pushed me to gravity, I would have thought it was much more scientific. It was much more, this is part of the question we're asking ourselves and part of the development. But it's true that as I was writing the book and I was trying to understand a little bit how my own exploration was fitting, my own personal story was fitting with the scientific exploration, I realized that it was there. It was always there. And I think part of it is that I think it's part of everyone. I think we all have a love for gravity, but we just don't. Maybe we forgot it or we don't know it. But to me, I can remember periods in my life where really this embracing of gravity and this feeling that it does connect us. It does connect us to the ground. It keeps us grounded. It keeps us there. It's something quite reassuring about it, but also something quite constant, quite universal. So it is, to me, growing up and throughout my development, it was very much that aspect of something which you can always rely on, which I very much loved about gravity. I think as a scientist, now you realize what you mean by that is the fact that gravity is universal. Gravity really connects us all. There's no one who is shielded from gravity. There's no one that gravity leaves and doesn't connect with. So this universality of gravity, the fact that it's a phenomenon that is connecting us here on Earth, but connecting everything in the solar system, everything in the universe, and not only right here, right now, but throughout the whole history of the universe, is something very fundamental that once you start thinking of it like that, you wonder, why would you think of anything else? There's nothing else to think about. There's just gravity is everything. Space-time is everything. It does connect us all to such a fundamental level that nowadays I can't even imagine not wanting to be driven towards gravity, because it's the ultimate quest of everything. It sounds a little bit arrogant. It sounds a little bit like I'm overselling it, but it is true. It is absolutely true.
Absolutely, as you say, right? Without gravity, the planets will not form, and stars will not light, and so on. Pretty much everything that we can, we can stand on, literally, is because of gravity. But looking at gravity from physics point of view, is you know when you from high school physics onwards, you feel like gravity is so well understood, everything is solved, and it has been so successful in all the prediction that we make about gravity. It has been tested again and again to different levels of precision, and it always holds up, and headline always ends up being Einstein was right. Every decade people find a different way to come back to the same headline, and yet it's a pretty serious area of study. So what are things about gravity, that requires the kind of research you are involved on? What are the unanswered questions that you hope to answer yourself and the field overall in coming decades about gravity?
So one very concrete question that physicists have been asking themselves almost since general relativity itself, almost since Einstein came up with the theory of gravity as being the manifestation of the curvature of space-time. It was understood already very early on that there's some regimes where our description of phenomenon using the curvature of space-time through general relativity stopped making sense. So very quickly, right after the formulation of general relativity, it was understood by Schwarzschild, for instance, that there was some solutions, some possibilities in that theory that black holes would exist. And black holes are very obscure objects. Nowadays, they have been observed, so they're not abstract at all. They're not just science fiction. They're not just some mathematical artifact of the model. They are reality. We know there's a black hole at the center of our galaxy. This is just amazing. And we know what happens when black holes merge with each other, and they produce some, not light, but they produce some fluctuation of space and time, some waves in space and time that propagates through the universe, and we have to observe them here. So as you say, general relativity, gravity has been tested with absolutely amazing precision. Everything we do confirms general relativity. And yet we know that it also confirms the existence of black holes. And black holes can be themselves described using Einstein's theory of general relativity. We can even describe what happens when you enter through a black hole, but there comes a point at the very center of the black hole where we know we can no longer use Einstein's theory of general relativity to describe what happens there. We know that the curvature is so dense. We know that things are so dense that we can't use the laws of physics as we have them at the moment to describe what happens there. And so we know we need a new formulation of even understanding what goes beyond the formulation of space and time to describe some regions that do exist in our universe, like at the center of black holes or like at the very beginning of the universe. This is one of the most fundamental questions that humanity has asked themselves since ever. Where do we come from? And that question has had many different facets and different ways to look at it. But fundamentally, the question is, where does the universe come from? Where does even the notion of space and time, where were they born? And those questions are so challenging to understand. We need to rephrase them. And we need to do it in such a way that doesn't rely on the presence of this framework of space and time. We are very human, so however we ask ourselves questions, it sort of assumes some notion of space and some notion of time. When we ask ourselves, where does the universe come from? There's a question of where and when, at the Big Bang, at the beginning of the universe. Not to even phrase those questions without a notion of space and time makes it very challenging. And so this is one of the areas of very, very active research nowadays, not just by me, but by really a lot of people trying to understand how to think of gravity in a very dense region of space and time, and how to unify it with the other fundamental forces of nature at the quantum level. When you think of it not just as a classical phenomenon, but really as a quantum mechanical phenomenon with its own laws of probabilities. So that's one big aspect of research, which is, I think, really some big driver. In one way or another, we're all trying to be part of the solution towards understanding that.
Got it. So you're saying, if you want to answer these fundamental questions about who we are, where we come from, how did our universe start, and even what's going on in the universe as we can see today, until we have a deeper understanding of gravity, we will not have satisfactory explanation.
Yes.
And I have some follow-up questions, on that. But let me just backtrack for a second. In the context of gravity, we talked about that, massive objects, tends to curve space-time. Can you help explain, people who may not be familiar with that, what does curving of space-time even mean? And even if you try to visualize curvature of space, what does, curvature of time, can possibly mean?
Yes. Yeah, it's difficult, particularly with no. So I think the first thing to say very concretely is that when we say those things, some people may have the impression that we, as theoretical physicists, have a ultra ability to conceptualize this in our head, and that they are missing something. You may have the impression that you're not able to picture it in your head in the same way as we do, but that's not true. It's not. We are all human, and we're all used to thinking of space and time being disconnected, because this is the reality of the life we are in. We don't typically unify them both. So to think just of the curvature, or let's say just space to start with, we often draw this picture of thinking like the surface of a trampoline, and then you imagine you have a ball in the middle, and so it will deform the surface of the trampoline. That picture is not perfect. It has some flaws, and it's not exactly what happens. But mentally, it's as good a picture as we can provide without starting to go through the equations. I mean, one of the key aspects there is that when we think of the surface of a trampoline, and then a ball that sits in the middle. First of all, the ball is deforming the surface of the trampoline, not because so much of its own mass, but rather because it's attracted by the Earth. So, and that's not quite what happens. There's not in the universe. It's not like there's another mass that things are attracted to. So it's in itself that the structure of space-time gets deformed. And then in the picture of the trampoline, where it's very challenging for us to visualize, or to make it more concrete, is that we have the impression that the surface of the trampoline gets deformed into another space, which is the height of the trampoline. Whereas for the universe, there's nothing other. There's not another dimension in which the universe is curved. The universe is everything. And so being able to understand what it means for the universe to be curved within itself is something I have no mental picture to give you other than sort of going along with that. But that is also already the notion of space. As you say, adding the notion of time and unifying space and time together is something quite tricky. But we know, for instance, that it curves time. One way to think of how it curves time is more, the notion of curvature is very much how you connect points with one another. So if you're thinking of the ball in a trampoline and deforming the surface of the trampoline, what happens is that it gets stretched a little bit. And so the fabric of the trampoline, the way the points are connected with one another, they are a bit pulled apart closer to where the mass is. So you can think of it like that. Now, in terms of what it means for time, to stretch time or to curve time as well as space, you have to think of how you connect points in space and in time. And that is simply the flow of time. The way we connect time together is just the way we experience the flow of time. It's not something we have control over, but it's something that we know. Time is flowing, and so we're connecting all the time. We're connecting points in time together. Now, how we do that for you and me here on the surface of the Earth will be very different to how someone else is doing it somewhere else in the universe. So for instance, someone else on the moon will experience a flow of time slightly different as compared to what we experience. Actually, time will take a little bit faster for someone sitting on the surface of the moon as compared to us. Not very much so. So it's hard on everyday life to experience that, but still, it is there. It's something that we can measure. there has been actually one of the first experiment already close to 100 years ago for that. People were taking atoms, which tick the very specific regularly. They emit, they decay, and so you can really think of them as a clock, extremely precise clock. And you take some atoms, radioactive atoms, at the bottom of a tower, and you compare with how they radiate at the top of the tower, and the radioactivity decay between atoms on different sides. And because they experience the curvature of space-time, because space-time is curved, and so the way points are connected together in time at the bottom of the tower is not the same as what it is at the top of the tower. They experience a flow of time which is different, and they behave differently, ever so slightly differently. And this difference has been measured. It is something real. It is something that we are using nowadays. It is something that we are now taking into account. You and I communicating right now, we are taking into account this slight difference in the flow of time,
right.
This curvature of space-time in a solar system. We are actually accounting for it right now. It's part of our everyday life, which is incredible.
And what's also incredible is that, as you were saying, that we have been able to measure it so precisely, and we understand, as you get closer to more and more massive objects like sun, or I guess anywhere close to even more massive object like black hole, time just keeps slowing down. In fact, problem guessing on the surface of black hole, just very close to it, almost slows down to probably a trickle. Just won't, few hours may pass, when you're very close to black hole, while centuries may pass when we are on Earth. It's almost some ways, as gravity gets stronger, it is able to kind of hold back time in some ways.
Absolutely, that's what it is. The notion of how we experience time is different, and gravity is really very much what keeps us, holds us back, or allows us to experience things together. That is absolutely true. And so that's why for light, for instance, for a photon, the particle of light, it doesn't experience the flow of time at all. For a photon, it's forever young. It doesn't evolve in time per se. It doesn't feel the flow of time. And so indeed gravity is very much encoded in how we perceive reality as a whole, which is very profound, I think.
Right. And so on one hand, we understand, how we know so much about gravity, but going back to what you were saying earlier, is there are things about gravity we don't understand today, and which is where and looks like, would you say in last few decades, the research around that has in some ways picked up? Because at some point it was, what was known was well understood, and what was not known was kind of parked. It was, people were busy with quantum mechanics and other things and so on. But now there's a renewed interest, and you are kind of very much in the middle of just figuring out. And, and do you think the field as a whole is starting to make progress? Is our understanding of gravity getting any better?
So I think, interestingly, from my perspective, and I think you probably will hear sometimes the opposite, but I think interestingly, the fact that we haven't detected new particles, for instance, in particle colliders, we haven't detected physics beyond the current realm of things, have freed us a little bit to think with a grander picture, and not being committed in a particular model, not chase after specific ways to formulate the world, but rather having a much more open mind of all possibilities that can be present, and follow them all in a much more systematic way, which I think is a way to make progress. It is important to remain relatively agnostic in how you want things to get realized at the end of the day. It's not about what we think looks pretty or not. It's about allowing to explore every possibility. And so this actually has freed us a little bit in exploring much more systematically in this type of aspect, from the quantum gravity perspective.
And right. And are there any developments? And at some point, I think you can also, talk to you about your work as well. Do you get a sense of progress? You think, we know more than what we knew, or at least better problems, if not better solutions, and reason for optimism in coming decade. I know theoretical physics is very slow work, and one should not ask for progress in years, but decades probably. Just what's your perspective? How the field is moving.
So I think we are, even though it's difficult to communicate some of those progresses with the public, and sometimes it's easier to say we made this discovery, we discovered that particle, we discovered gravitational waves, and those are big headlines. These are easy to connect with. But some of the development we are making in theoretical physics, particularly in connecting with quantum gravity, or a theory of everything, they are a little bit more abstract, but still we are making a lot of progress. We're making a lot of progress in connecting the world as we're experiencing it now with an ultimate theory of everything. And that is something very profound, because you're making connection between what you can probe and experiment with things that we will never have access to, and yet we're making a line of communication. It's very, very abstract. So that will take quite a while to take, and being able to see what the consequences are and being able to articulate it in a way that everybody can understand and embrace it. But it doesn't mean that progress isn't actually being driven in those areas. And it is quite exciting.
Yeah. Yeah, I can see all those mathematical symbols behind you on the board. It's so very exotic and very difficult to understand. But maybe you can a little bit talk about what does a day-to-day life of a theoretical physicist look like? It's on some level, you're talking about very deep, fundamental understanding of what we know today, how the world works, as well as very sophisticated questions about what we don't know, where things break down, and so on. So what does your life on a daily basis in grappling with these problems look like?
Yeah. So I have to admit, there's a lot of things we don't, embracing things we don't know. There's a lot of things that we try out, that I try out. I wake up. A lot of the time I wake up in the morning and think, oh, shall I try this? And I try, and I talk with students, I talk with postdocs. We try some particular direction, and we realize, no, that's just not working out. It's too challenging, or simply that's not doing what we thought it would be doing. And that in itself, sometimes it's a bit painful. It's a little bit of the beauty of falling, but it is important, and it's part of connecting everything together. It is extremely important. So you do understand so much more. You build your intuition. You understand actually how to organize and structure things so much more by realizing what is actually not working out and why it's not working out. And then that's being part of the solution, because once you understand why things behave in a particular way, you can try to accommodate for that. And sometimes you really need to take a step back and say, okay, let's start all over again. Rather than doing that, we're going to be doing something quite different, but you learn from that. I think my research, I'm at that stage of my career where I can take more liberty in addressing those questions. And if I've been working for 3 years on something and it doesn't work out, I can still think, okay, well, that was good to think about it, and I learn a lot from it. But I'm working also with students who need to graduate with a PhD or graduate with something at the end of it. So then you also need to be much more pragmatic and structure things so that they can make progress. They can have interesting questions to explore so that they can move forward, and then later on start tackling deeper questions. So there's always a little bit of a balance between having some questions we're exploring, which are relatively concrete, and not necessarily straightforward, but relatively concrete, where we know roughly where we headed there, and then embedding this in a much bigger question. So I think it's a little bit, you can see the blackboard on my back, but it's a little bit like if you imagine you have a big painting, and some of the time you're working very specifically on a particular detail, and this will work out. It's going to be very pretty. But then there's a much bigger picture you're trying to paint, and it's not entirely clear how the little features will connect out together. You have some ideas in your mind, but a lot of the work is to discuss with people to see how all of this will ultimately make sense as a whole painting, as opposed to disconnected points with one another.
Right, got it. So it's like, maybe one way to say this is like a big complicated puzzle that you're trying to solve, and they're able to zero into some aspects of it, saying, okay, let me engage with some of the PhD students and solve this part of the problem, but the bigger picture may take probably a much longer period of time to figure out. But science, as much as anything else, is also very human endeavor. At some point in your book, you talk about, you had some very deep insights about potentially modifying general relativity, and you had, pretty high profile publications around that. But it was met with, lot of resistance and lot of not so receptive, welcome, which was somewhat surprising and taxing, and you have to kind of plow through that.
Yeah.
Just talk about that experience, when you're trying to do as it is, coming with new insight must be very hard. And when you think you've got to something, then you have to in some ways, communicate, and, face all the onslaught of objections from all corners.
Yes.
Can't be very motivating.
So it's true. No, sometimes you really need to make sure the drive is coming from yourself, because there's a scientific process, but as you say, we're also all human, and so there's a level of ego that may come with some people than some others, and you need to be able to deal with that as well, for better or for worse. I think some level of skepticism is important in the scientific process, because we can't just start all over from scratch every day. We wouldn't be making any progress. So if someone comes along and say, hey, look, I have something new here, how about we think about that? It is normal to some extent that we start wondering, okay, hold on a second, have you thought about all of the things? That in itself is acceptable. I think it is true, though, that there is also a level of being defensive. But what I have found is that there's also some level of culture, not geographical culture, not country culture, but scientific culture, mathematical language of way to phrase things in your mind. And so to start with, we had developed some understanding of how to go beyond Einstein's theory of general relativity based on our way to articulate things. It's all mathematical. We're all talking with mathematics, but even in mathematics, there's different ways to address the questions. And so even in presenting this in completely mathematical terms, one can imagine that if we present it to someone, they will start with the beginning and then try to follow a procedure and understand whether or not it was correct. And if they had done that, they would know it was correct. But most of the time, that's not quite the way people work. They have some intuition, they have some way of phrasing things in their mind. And so rather than doing that, what they would do is start with a starting point and then have their own logic in their head, their own language, their own arguments in their head, and then come out to a conclusion which was contradictory to ours. And so it took us years and years to actually translate everything we have done in different languages, in different mathematical languages, in different cultures, so that someone would have an argument and say, see, it doesn't make sense because of the argument, I can present it to you. And rather than us saying, but look, it makes sense in our language, which wasn't making connection, we had to sit down, learn the language, adapt to them, translate it in their logic, and show it in their language how things were evolving so that we could reach an agreement. And that we could do, we've done it for years and years. And so it did require a lot of motivations, because we can do it once, we can do it twice, we can do it 10 times. But when it comes to the 20th time, you may think, well, trust me now, just trust me. But it was part of the process as well. And I think it did make us all much richer conceptually in seeing how all of this was connected in people's different way of thinking. And that is important.
That's amazing. I think, a lot of us, we don't realize that level that, the scientists, have to go through, both in terms of, really wrestle with very, very complex understanding of the universe, try to find a unique insight and breakthrough, figure out that all the maths needs to work, and then you have to communicate and convince the field around you and overcome the resistance. So at this point, all I can say, I obviously don't have the ability to ask you to explain the math, but I can just communicate my appreciation for what you and other scientists do. In some ways, kind of fighting the battle on behalf of all of us, because we can all enrich our lives with better understanding of where we come from, how does all this work, and love to see some of the unsolved questions make progress in our lifetime. So I think it's incredible that, the kind of investment, Claudia, you and other scientists do. At some point in your book, you also talk about, just we are also not exactly in a great shape when it comes to women in physics as well, that it's another area which is very much a work in progress.
Absolutely, yeah. And I think that is true that it depends on where you are in the world. But as a whole, and at my level, in terms of being a permanent researcher, being a permanent scientist in theoretical physics, there is not as many women as would be actually beneficial for research, beneficial for the driving of research. I think a lot of the time we have the impression that the reason we want more women in physics is just to be nice with a woman. That's not the point. That's absolutely not the point. The reality is, if we address questions in a more diverse way, we will make more progress. So doing research in a more diverse way is just pragmatically the best way to do research. That is the bottom line. This is the reality. So if we're not as diverse as we could be, if there's not as many women as there could be in research, particularly in theoretical physics, we're not actually driving the research and the progress as well as we could do. So there are a lot of reasons why this is very slow, and I've been doing a lot of work at every level in trying to engage much more with women at various different levels. But it's true that we're still in a situation where, first of all, there's not many women, and the fewer women there are, the more challenging it is actually for the women. And it does require a constant need of self-motivation, which sometimes is a little bit mixed in with some level of self-questioning and needing to justify your existence, needing to justify your presence in the field and the progress that you made in the field. And this is something, again, you can do it once, you can do it twice, but after a while, you may wonder whether you're asking too much, whether is it really fair to keep needing to repeat this justification over and over again. And I can understand that for some people, being man or woman, they realize that if it's going to be like that, they may not want to play along. You want to play along if you feel welcome. You want to play along if you feel like you can contribute and to some level feel valued. And I think people are valued. Every contribution is valued, but there is sometimes a little bit of ego, which means that this value is not presented, is not reflected as well as it could be. And I think that is for us as a whole to change the culture. It is for us as a whole to see that we can make progress in science and in theoretical physics in a much more inclusive way, which is beneficial for all of us. And I personally would have enjoyed that. I would actually enjoy doing science in a little bit of a more inclusive way. I think most people are very much on board with this, but when it comes to the implementation, there's still little steps, little obstacles, which each single one of them is not a big deal. But when you add them all up together, in the end, it does become a little bit tiresome.
Yeah, I know I can. Yeah, I read a lot about history of science, and you keep coming across these stories of, even all the way up to Nobel Prize, also so many stories of discrimination, so many women, who not only contributed to sometimes, led a particular outcome, and they were just, blatantly ignored. And that's, it's just so painful to even read, and let alone being in that situation, to be in that such a unique situation. Jocelyn Bell, one example.
That's
I think
right.
the person
Exactly.
who was involved in the deciphering of DNA is the other person, many others. So I think,
Exactly.
I think, we need to make progress on science, but we also probably just understand human nature and cultures and society and all that itself is also very much work in progress, and hope we make more faster progress there.
Exactly. Exactly. No, you're absolutely right. And it's all part of the same thing. It is absolutely.
Right. And so Claudia, I mean, other than, your earlier foray into like deep commitment to pursuing, trying to be an astronaut, and then, pursuing theoretical physics at the highest of levels, you also make an effort to reach out to people, both through your book, your public talks and you work with various schools and so on. So just talk a bit more about your motivation and drive for just going out there and communicating the joy of science to public at large.
For me, one aspect is really sharing a little bit the excitement of what we do. It's almost selfish to some extent because for two reasons. First of all, if I share the excitement, it makes me more excited myself, and I like to see other people realize that it's very beautiful what we're doing, and it's not for us, it's for all of us. I think that is important. The other slightly selfish reason I'm doing it is because I would love for us to do science, to do theoretical physics in a more inclusive way, in a more diverse way. It would make the environment much better. And so that is, of course, it's a little bit selfish from our perspective, but I think it is for the best for everyone, because it's the best way to do that. But it is very conceptual, it is very abstract what we do. And sometimes it's easy to get lost in some of the details and lose the bigger picture of what is it we're trying to achieve, where are we headed, and there's different levels in those questions. But I think engaging with the public and trying to coordinate a little bit, go back down on earth and realize what is it that drives us all together in those fundamental questions is essential. Sometimes the simplest questions are actually the deepest and actually the most profound. Sometimes you have kids raising their hands and asking a very, very deep questions and realize this is the question. This is really how we should think about things. And we just overcomplicating everything. It may sound a little bit naive what I'm saying, but it is true. Every time I teach a course, so we teach as well, and I think that is important. When you do research, you also teach. And of course, I teach concepts which I know very well about. I'm supposed to be an expert on that. I know very well. I don't really need to remind myself of any of the equations or anything. But still, every time I teach it, I lecture it, I reformulate it a little bit, or I make connections in discussing with the students or in how I present it, which makes me realize some things which I didn't realize before. And so it is very powerful. But really, the real reason I like going to schools, I like engaging is because there's so much, as you say, there's so much beauty in what we do. It's part of sharing that aspect. If we just did it ourselves in a corner with never sharing it, I think there would be no value to it. The value of what we do is in being able to share it with others.
Oh, that's amazing. I'm really glad to see the effort you put in that. I think, last couple of years, I'm also trying to learn about state of Indian science. And we have, some amazing institutes, lot of outstanding scientists, but the public outreach effort, fairly limited so far. And I hope, that also changes because, if you think about a series like Cosmos, the Carl Sagan did, it inspired a whole generation of kids to potentially pursue career in science. And science, by and large, pretty much all parts of the world is taxpayer funded. So people also understanding of, what do we get out of, this investment, whether it's a deep understanding of universe or moving technology forward and so on. So I think it's a very important part of at least some portion of science establishment needs to take it very, very seriously.
That's right. And I think it's also part of the thought process. It's about science and the question we're exploring in themselves and what we're trying to drive in themselves. But it's also how we address those questions, which then structure how we are as a society. And that's very, very important. We can't make just random decisions through our societies and how we evolve. It is important to have this understanding of how things are structured, have this logical thought process of how things should evolve to make decisions. I think this is important at all levels. And so you see scientists actually, and physicists in particular, after they study physics at any level, then actually infiltrate every aspect of the society. And they have a very impactful effect at every level because it's important to analyze things in a particular way and to evolve in a particular way.
Right. So that's another work in progress. But I want to go back to your book for a second. And one thing I was not expected to find in your book was, your description of gravity having a sense of humor. that's, that obviously made the book very light. And you have a point also about people somewhere so subtle, and it's been kind of teasing, I guess, is what you are hinting at. But why don't you describe, why do you think gravity has this mysterious sense of humor?
Yeah, I think I'm trying to provoke you a little bit, and I'm glad that succeeded maybe a little bit. So I think it's part of the same thing to start with, of why I wanted to present it like that. That we're almost scared of gravity. It's something quite serious in some sense. We play with it when we're kids, and we know it's there. But after a while, I think as we grow, all of us, we started getting a little scared of it. We think of it as being the law. There's Newton's law, and there's this rigidity, some level of seriousness in gravity, in how it's present, and we can't challenge it, and we can't confront it to some extent. And I think that rigidity is wrong in the scientific exploration. We should constantly challenge ourselves and understand of nature. It is important to do that. For gravity, it has an even a different connotation as well. In addition, which is that so gravity, as described by Einstein in the theory of general relativity, is something extremely serious in that it has no limit to it. It has no limit to its seriousness. It has no limit to how it connects to everything, but so seriously, so rigidly to everything and everyone, it's almost to its own detriment. And that's part of one of the biggest questions, I would say one of the most embarrassing questions of modern science, which is the cosmological constant problem, or what you might have heard as the vacuum energy, the quantum vacuum energy problem, or the dark energy problem. All of those are related, and it's a huge question. It's a huge embarrassment. And it is an embarrassment if you take seriously Einstein's theory of general relativity in its ability to account for every single contribution to nothingness in the whole of the universe. And that in itself relies or is a consequence of the rigidity of Einstein's theory of general relativity. But in principle, it is possible to let it go to some extent. Not I don't want to modify Einstein's theory of general relativity to the extent that things would be different in this room or in the solar system or in the galaxy. But with the current cosmological observations, we rely on Einstein's theory of general relativity to understand how the universe is evolving. So we're looking at the universe through specific glasses, through specific lenses, which are the tools of Einstein's theory of general relativity. But we don't know whether or not this is correct. We don't know because we haven't been able to test Einstein's theory of general relativity on those scales. And it's possible that this is tinted, and actually there's much more creativity, there's much more humor in Einstein's theory of in the theory of gravity, and that's what I mean by a sense of humor. It's an ability to let go. It's an ability to relax this level of seriousness that Einstein's theory of general relativity has, and that is a theory of massive gravity that my collaborators and I have explored. And my idea is not to think, okay, here's a competitor to Einstein's theory of general relativity, and Einstein was wrong. That's not at all the idea. That's not how we do science. It's not about saying someone is right, someone is wrong, and winning a race. It's not about that. It's about exploring the possibilities and seeing how can we think of the world and how you would compare. And then nature will tell us at the end of the day. We just need to allow for possibility to be there and just embrace things and take our ego out of the equation. Just let ourselves go to the different possibilities. So it's part of this free fall. Let's just accept these different ways of thinking about it, and then we'll see what happens. But that in itself requires having a little bit of a sense of humor as well, accepting that sometimes you will be wrong, and that's okay. You just laugh about it. That's okay.
Right. So in your both in your research and in your book, you're in some ways you're hinting at, universe is a vast place, larger than pretty much, our capability to imagine. And therefore, we don't necessarily need to assume that gravity works exactly the same way, irrespective of scales involved. It can possibly behave differently as you get to a different order of distances, and that can lead to possibly new physics, which can maybe explain, because as you say, there's so many things are today we don't have a comprehensive understanding. They're all known mysteries that both laymen and serious scientists alike, we wonder, what could be hiding behind all that, right? And a possible modification of general relativity could offer some clues. And one of the tools that have developed recently, and you talk a lot about in your book as well, the idea of gravitational waves. In fact, you have coined the term glide. So maybe you can talk about that. What are gravitational waves, and why does it make sense to think of those as one type of light, with the prefix of G?
Yeah, that's a great question. So I think, let me start with the second part, which is why do I call gravitational waves glide, or like light with a G, glide? And the real reason is to make it realize that it's something we're quite used to. When we talk about gravitational waves, it may sound a bit abstract, it may sound a bit technical and scientific, but in reality, as a concept, we are relatively used to it. At least we're used to light, and gravitational waves or glide is not so dissimilar to some extent as light. The difference, of course, is light. They are waves of an electromagnetic field, of an electric field, a magnetic field. So they are waves of that traveling through space-time. It's not going to be very big, but I will distort space and time a little bit around my hands, just because my hands have a mass, they have energy, and so they curve a little bit space and time. And when I shake them, that shakes space and time a little bit, and so I produce waves very much in the same way as if I throw a stone on a pond. It will create ripples on the surface of the pond, and they will propagate like that. So of course, we can't visualize them quite in the same way, but to some extent, when I do this with my hand, I do produce tiny, really tiny gravitational waves that propagates through space and time. Now, my hands are not very heavy. They're not very massive, I should say. So you really need very massive objects, very dense, very close to one another, to produce gravitational waves of light with sufficient amplitude that we can hope to observe them really, so that the distortions of space and time are important. Otherwise, with my hands, the distortion of space and time is not very important, which is lucky. Otherwise, time would start flowing in a different way. Space would be distorted when I do that. But black holes, when they merge one another, they produce gravitational waves. They emit gravitational waves. We can say that they radiate energy. So just like the sun radiates energy through light, so black holes, when they merge, they radiate energy through also gravitational waves, through light. Now, those are very essential to detect, and they have been detected. Gravitational waves have been detected. But you can think of it as a new way to see the universe, to see it with almost a different color. Just like all light we have received is a particular channel, is a particular way to communicate with the universe. Light, we should just embrace it. It's a new way to communicate, or at least it's a new way to see, to observe the universe. And that it would allow us to observe the universe, to observe how the gravitational waves, what they have propagated through along the journey to us, to reach us. And whatever they propagate through, for instance, dark energy, can have an imprint on them, can affect them. And so it's essential for us to observe those gravitational waves, and that will allow us to have a much better picture of the whole of the universe. And that's why they are huge. There's been some interferometers here on Earth that have detected gravitational waves, but this is a huge prospect for the future. There's a space interferometry, the space, like the LISA space interferometer that's going to be, has been approved, that's going to be launched. There's some observatories on Earth otherwise trying to look at imprints of gravitational waves in the sky in different ways. And I think this is going to be huge for the future, because it's really, think of it as a new way to see the universe in a different color. So I'm very excited about that. It's very much about a new way to see the world in a way that we hadn't even thought about before. So the possibilities are almost endless with that. It's going to be amazing. I'm very excited about that.
That's great to hear. And as you know, as you're describing, I think with the LIGO first detection in 2015 onwards, I think we now routinely are getting more and more signals. And in fact, one thing I would like to mention is one of the legs of LIGO is being planned for India, and I think construction has recently started. So hopefully that will be operational next 4 or 5 years, and India will start to make its own contribution and detect probably some more interesting gravitational waves. In addition to LISA, I think that will detect probably lower frequencies, which will help understand different phenomena. So hopefully all this provides us enough clue to kind of spur science along and give a lot more data to work with, and probably make a dent, and maybe, who knows, at some point actually modify general relativity, which will be progress for humanity. It's not about proving anyone wrong or right. But this is, Claudia, this is fascinating. I know you are potentially planning a trip to India as well. I hope you are able to make that trip. But it's great to, I think your journey is very inspiring, especially I think for youngsters, that you can actually pursue your dreams. As you do dream of becoming an astronaut or anything else, you can put serious effort behind that, pursue that systematically, commit yourself to that. Your journey is inspiring. I think your book is very easy read, fun read. You learn a lot about science, but about your journey and, some life lessons as well. So I'm just want to thank you for taking the time and speaking there. And look forward to staying in touch, Claudia. Thanks.
Thank you.
At SparX, we aim to bring to you stories of exponential impact. We share in-depth analysis of what goes behind success stories. If you find our conversations interesting, you can join us by subscribing to our YouTube channel. You can also listen to SparX on Spotify, Apple Podcast, or any other audio platform of your choice. If you have any suggestions on who we should invite or what topics we need to cover, just let us know in the comments. We are always listening, looking for ways to improve, and keep getting better as we go along.